Good evening. This is not the last lecture, but just the one before. So we have to see many things, and still next week we have to learn many new things, and then we can be on holiday for a few weeks before the next semester. Let me remind you what we did last time. I just briefly introduced this notion. It's good to know that you can consider functions with value in a Hilbert space. And now, for such function, you can discuss the notion of continuity, differentiability, and so on. But you can either do it in the strong way or in the weak way, because we have seen strong convergence and weak convergence on H. And the same, you can define Riemann type integrals, like you do for Riemann integrals. And you can discuss when you do Riemann sums, you have a sum, and you can discuss the convergence of this sum either in the strong sense or in the weak sense. But the important inequality is that whenever you do such an integral, when it's well defined, most probably you need a continuity of the function. This is an element of H, so you can take its norm, and there is this inequality that this norm is smaller than the integral of this number. So it means you take the norm for each point x. This is then a positive number, and you take this integral. It's quite similar to what you have for Riemann sum, except that it would be with value in R or in C, and this would be absolute value or modulus. And the same we can do functions with value in B of H. So at every point you have a matrix or an operator, depending on the size of the Hilbert space. You can consider these Riemann sums. Now this integral is an element of B of H, and we have a similar inequality. All right. Be careful just of one thing. If you take two functions with value in H, you cannot define a product, because phi1 of x times phi2 of x, you don't know the meaning. But if you take psi1 and psi2 in B of H, then you can multiply two bounded operators. So this is meaningful. All right. This is just a first reminder. I will not speak about this probably anymore. This topic is important. First, we have seen bounded linear operator. Now we look at general linear operators. So it's a pair. So you have one subspace, so subspace of H, and one operator acting from D of A to H, and it's linear. You can do it because if this is a subspace, you can do an addition. It's a vector space. This is also a vector space, so it's meaningful to apply A to a linear combination, and you get a linear combination here. We have this notion of extension of restrictions. I don't really recall the details, but you can have the same operator with different domains. So if this, we write this, if this one is an extension of this one, meaning that this domain is included in this one, and when you apply A on element of D of A, the same as applying B on the same element. Or this one is a restriction of this one. And I spent some time on one example, which is this multiplication by X in the Hilbert space L2 of R. So we take functions which are square integrables, and we multiply by the variable. It's a linear operator, but it's not a bounded one, so we need a domain. Otherwise, of course, you can still consider xf for any f in this space, but you are not sure, if f is arbitrary, you're not sure that this is xf is still in this Hilbert space. It might be in something larger. All right. Okay, we have also seen that if you start with an expression like this, and we suppose that this domain is dense. Dense, remember, it means you can approximate any element of the big domain by an element in this one up to an error of size epsilon. So if this is a dense domain in H, and if you have such an inequality for, so B of F takes a norm is smaller than C times norm of F for all F in this domain, then you can extend this operator in this sense to the entire Hilbert space. So it becomes a bounded operator. Otherwise, if there is no such C, it's really an unbounded operator. And we have shown that this one is an unbounded operator because if you apply f to x to a certain family of function, you can get numbers which are bigger and bigger. I did this last week. Now, there is just a technical notion which is, it's important, but for us, I don't want to put too much emphasis. This notion of closed operator, if you choose different domains, some are better than other one. And a closed operator is when you choose a domain with a very good property. But this is slightly technical. On the other hand, what is very important is this notion of adjoint. For operator in B of H, we had this notion of adjoint for any operator. Now, and it's also a bounded operator. Now for starting with AD of A, which is not bounded, defining an adjoint is always possible if D of A is dense in H, but it's less straightforward. I mean, I gave you a definition.
Are you recording?
I am recording or not? Nobody remind me this.
Well,
yes, I am. It's recording. Thank you. No, it's good to check. So I gave a formula for this adjoint, and it's going to play an important role because in a minute I will speak about self-adjoint operators. Evaluation. This is always something I need to do at the end of the semester. On NUCT, so this is only for Nagoya University students. Oh, no, it doesn't exist anymore. Now it's unpacked. Okay, on this website, you need to evaluate, I don't know if it is all your courses, but many courses. Please don't forget to do it. It takes you a few minutes, but it's important for us. Maybe not for you, but for us. The administration asks us to remind it to you, but also they use this information. So please, whenever you have time, do this evaluation process. All right. Okay. If you have any question, you can always interrupt me. Otherwise, I will continue based on this notion of adjoint. There is a first result, which you have probably seen in linear algebra. Property of the adjoint, because it holds also for matrices. The kernel of the adjoint matrix or the adjoint operator is the same as the orthogonal of the range. This is an exercise. You can check it. You use the scalar product, check the definition of the adjoint. So this is a useful property. You know what is a range? This is a set of elements that you reach when you apply A. Be careful. This is a set of AF for any F in the domain of A before taking the ortho complement. But then the ortho complement is a set of elements so that you have a scalar product which is 0. So you can easily implement the adjoint. I let you check this. And there is a second property which is also important. If you consider this notion of extension, if A, B of A is included in B of B. So remember, it means that D of A is a small set, D of B is bigger, but when you apply either A or B on the small domain, you have the same thing. So if A or if B is an extension of A, then what about the adjoint? Because you can, I assume that they are both densely defined. I should mention it. Densely defined. If D of A, D of B dense in H, In fact, it's enough if I assume that the smallest one is dense, because the other one will also be dense. But then you have the relation between the adjoints, and it's going in the reverse direction. Okay. But this is interesting because look, I already mentioned we want to take the biggest domain. So you are interested in if we consider this expression X, we can define it on the test function or on the Schwarz functions or on something bigger. So you can always check and try to find a bigger space, but it means that the adjoint is becoming smaller because the adjoint of the big set is included in the adjoint of the other one. So you have this reverse direction when you take the adjoint. And in fact, this is meaningful for the next definition. You would like to find an optimal, and the optimal is precisely the notion of self-adjoint operators. Densely defined. By the way, if you want to check this, you can also do it with just based on the definition. You check what means the definition, and you can end up with this because you have less vectors to control. A densely defined operator. A d of A is self-adjoint if A star d of A star. So if the adjoint, which you can define because I have assumed that it's densely defined, is equal to A d of A. And for matrices, it should remind you this is the adjoint of a matrix is equal to the matrix itself. But here, this is more precise because please observe that you need to have an equality between the two domains. The two domains have to be equal. And then on these two domains, which are now equal, A star has to be equal to A. Of course, if the operator is bounded, the domain is the entire Hilbert space. So these two would be the entire Hilbert space. You only need to check that A star is A. And this is already what I mentioned for bounded self-adjoint operator. Okay. And now an observation. We will deal with self-adjoint operators today and next week. If AD of A is self-adjoint, then we have this equality. AF G is F A G. But who are F and G, or where do they belong to? They have to be in the domain. Otherwise, it's not. If F is not in the domain of A, this is not well defined. If G is not in the domain of A, this is not well defined. So this has to be true for any F and G belonging to the domain of A, which is also the domain of the adjoint. So an operator is self-adjoint in this. On other consequence, you can check because of the definition of the adjoint, you get this equality. However, this equality is not the definition of self-adjoint. And this is a common mistake this is not the definition of a self-adjoint operator. Why? Because it doesn't say anything about the domain of the adjoint. It tells you you have such an equality, but it doesn't tell you anything about the adjoint. So it's not a definition of a self-adjoint. In fact, it is a definition of something. This equality means A is symmetric. Whenever we have an operator which satisfies this, we define it, we call it symmetric. We say it's symmetric, but it's not self-adjoint. So if you do a picture, if you have here the set of self-adjoint operator, the set of symmetric operator is bigger. Why is it bigger? Because, as I mentioned, firstly, any self-adjoint implies this, but the opposite is not true. So be careful, this condition is stronger. The condition of being self-adjoint is stronger than being symmetric. Yeah?
Is it possible that we have an operator that satisfies that, but then it satisfies something like it just doesn't satisfy this, for example, because let's say we have an operator B that is A in the domain of A, but not A in the domain of B minus domain of A. Think of B having a bigger domain than A.
Yeah.
And then but then it contains A, so it will satisfy that inequality in the sense of the thing. But B cannot be the adjoint of A in that case, no?
If an operator is symmetric, you are not sure that it is self-adjoint. You may have extensions which are self-adjoint and some are not self-adjoint. So yes, if you have a symmetric operator, this is a good thing. A symmetric operator can, but it's not always the case, can have one or more self-adjoint extensions.
That doesn't have to be the case.
But indeed, but it's not always the case. And this is indeed an important topic. It's not always the case. If I give you one symmetric operator, does it exist one extension, so a domain which is slightly bigger such that it becomes self-adjoint or not? Or do you have more than one? So can you find different domain such that it's self-adjoint? This domain would be, okay, now I was not planning to do it, but suppose A is symmetric, AD of A symmetric. What can happen? So I just represent the domain. It may happen that there exists a domain slightly bigger, so that B of B is self-adjoint. This is possible. But it's also possible that there exists a different domain still containing D of A, but slightly different, so that this new operator C, D of C, which is also an extension, can be also self-adjoint. I'm not sure the picture is not completely misleading, so be careful about this picture. But what I want to say is, yes, a certain operator with a certain domain can be symmetric. There may exist only one self-adjoint extension or more than one, maybe even an infinite number, or maybe no one. It's possible that there is no extension which is self-adjoint. So it depends. It depends on your initial operator.
But can we say that a symmetric operator is, sorry, the symmetric operator acts as its own adjoint in the domain of.
This is too complicated. I don't understand you. If this image, many things can happen. Yes. Yeah. Sorry? Oh. Self-adjoint, you know exactly something about the domain of the adjoint, while symmetric, you don't know anything about the domain of the adjoint. And in fact, yeah, symmetric doesn't tell you anything about the domain of the adjoint, while if it is self-adjoint, you know that the domain of the adjoint is the same domain. And then I'm going to state a result about self-adjoint operator, which is not true for symmetric operator. So self-adjoint operators have a very nice theory, while symmetric operators do not have. And in quantum mechanics, we always want to have self-adjoint operator. So what is true, and this is also a little bit misleading, you can check it. And it will become even more clear later. If A, B of A is symmetric, so in particular, if it is self-adjoint because it's a smaller set, then AF F is a real number. Just because if you put it on the other side, you get the same expression, and you know that on the other side, it is a complex conjugation. So it means this expression is equal to its complex conjugate. Let's check it. This is by definition FAF, because it's symmetric, but this is AF F complex conjugation, property of the scalar product. So it means this is real. Otherwise, you cannot have this. Okay. So this expression is always real, but it's not sufficient for being self-adjoint. And the theory is well developed for self-adjoint, but not for symmetric. You have problem for symmetric. In particular, what I'm going to define in the future, so today and next week, is not true for symmetric operator, it's true for self-adjoint. So probably this is new, the notion of resolvent on spectrum. You know what is the spectrum of a matrix? The spectrum of a matrix is just the eigenvalues. But this is not enough in our framework, because we can have continuous spectrum. I will come to this. So first, I need the notion of invertibility. A linear operator, like for bounded one, a linear operator AD of A is invertible if, remember, the kernel of A is only 0. So the set of F which are sent by A to 0, remember the kernel, this is a set of F in the domain, so that AF is 0. The only one is 0. 0 is always sent on 0, okay? And if it is, so it means in particular, it's equal, the same as injective. If you are familiar with this notion of injectivity, right? And we have seen for bounded operators, whenever it is injective or invertible, then we can define an inverse. But what is the domain of the inverse? Exists. What is the domain of the inverse? It's a range. So I will do a picture. What do I mean? You have the domain of A inside a bigger Hilbert space H. Then you suppose that these give you another Hilbert space, and the range is this. This is the range of A. Remember, the range is the image of this set by A. So suppose it's injective, so it means two different points will always arrive at two different points. This is a notion of injective. Then you can define an inverse A minus 1 from this set to this one. So A minus 1 is from the range. So the domain of the inverse is a range, and the range of the inverse is the domain of A. Maybe I can just write it. The range of the inverse is the domain D of A. This is the same story as for bounded. But when I spoke about bounded operators, I had not this notion of unbounded. So I couldn't say maybe the inverse is unbounded. Now we know what is an unbounded operator. No problem. It has a domain, and you define it like this. But it turned out that if the range of A is the entire Hilbert space, so it means the inverse is going to be defined everywhere, then the inverse is bounded. This is not straightforward, but then A minus 1 is in D of H. And do you want an example? Okay, we can look at an example. Consider L2 of R, the set of square integrable function. And let me take A equal to, we know X is not bounded, but I want to take X squared plus 1. I don't want to have negative things.
What's 1?
The number 1. After 0, you have 1.
Really?
Yes, but it's identity operator. In fact, we use the same. It's the same as 1 because X squared plus 1. Why I want this? Because I don't want something which goes through 0. But then what is the inverse? This is one of the exercises. What is A minus, of course, I need a domain, D of X squared plus 1. You can guess the domain. It is a set of functions such that when you multiply by this, it is square integrable. I don't write it. But what is the inverse? And I'm claiming the domain is the entire Hilbert space. What is the inverse? Can you guess the inverse? No, no conjugate. No, it's, so what is the inverse? Remember, you want to come back to the same place. So if you start here, you go there, it's multiplication by X squared. Okay. I use two different notation. I also use M of the function X squared plus 1. Multiplication by this function. So how it acts, maybe I should mention it again. How it acts simply. X squared plus 1 on a F evaluated at small x is simply X squared plus 1 times F of X. Multiplication. Now you want to have an inverse such that you come back to here. So the only thing you can define, A minus 1 on a F evaluated at X. Who can guess? Yes, 1 over X squared plus 1 applied to F of X. Because if In one direction, you multiply by this. If you want to come back to f, you need to divide by x squared plus 1. So this is the inverse. Is this going to be a bounded operator? Yes, you can check this number. AF, this is also an exercise, is always smaller than 1 times f. Why? Because this is always smaller than 1. It's in fact an equality. No, it's an inequality, but what you can easily get is that the norm of A is 1. If you are not confident, this is an easy exercise. Take the again, always look at the definition. There is nothing mysterious. If you look at the definition, you apply you have to be like a robot. You just look at the definition, input, output. It's not more difficult than this. But sometimes it's not so easy, but here, look at the definition and apply the definitions.
Are we allowed to give x to a complex number?
Yes, this function could be a complex function, but complex valued function. But here, no, the function can be.
The function can be complex valued, but x is a real number.
Yes, x is a real number, but the function, I could take the function. You're right, I could define A, it could be x squared plus I. I is of complex number. This is fine. But x itself is just a real number because I'm dealing with this. So the function can be complex valued, but x is always real.
So I is not in the domain, right? It's again
I is a bound. Yes, it is in the domain. Look at the definition of a multiplication operator. I is just I times f is evaluated at x would give me just if of x, and this is a bounded operator, so you have no problem.
But it's not invertible?
Please look at the definition. It is. What is the inverse of I? It's 1 over I.
It is minus I.
Because when you multiply I by this guy, you get 1. But yeah, before, just look at the definition. So we have this notion of what is an inverse of an operator.
That's not your laptop.
Thank you. So we know what is the inverse of an operator. And just a remark, if the inverse A minus 1, domain of A minus 1 is bounded, so it means in particular that the domain of the inverse is going to be the entire Hilbert space, we say that AD of A is boundedly invertible. I already mentioned this in the framework of bounded operators because it's the same, invertible. Okay, why I need this notion? Because I want to generalize the notion of eigenvalues. What happens for matrices and eigenvalues? Just a remark. If A is a matrix, how do you define an eigenvalue? This is just a parenthesis. If A is a matrix, you are going to define lambda is an eigenvalue if you have such an equation, right? And F is a vector. But I can also write A minus lambda F is 0. These two lines are equivalent, right, for matrix. And what happens with the second one? The second one, A minus lambda is not invertible because you have somebody, I assume that F is not 0. You have somebody in the kernel. So this is equivalent to kernel of A minus lambda, not empty, not just 0. You have F. Right? These three things are quite clear for matrices. Okay, if f is not 0, lambda is an eigenvalue. If you have the first equality, you can rewrite it as the second equality, and it means that k of a minus lambda is not empty. It contains f. So for the notion I'm going to introduce, I'm going to use a third line. And precisely, this is what I introduced with this notion of invertibility. And this is much more general than eigenvalues. So let's look at this definition. First, the resolvent set of the resolvent set of AD of A is the subset of of C given by, so it's denoted by rho of A. This is a general notation. This is rho, R-H-O. Rho of A is a set of complex numbers so that k of A minus Z, in fact, I should write A minus Z minus 1, A minus Z times 1. You subtract Z times the identity. K of A minus Z is equal to 0. So it means it's invertible. This is the same as A minus Z times 1 invertible. But this is not enough. Sorry, I should not close this. And so we know it's invertible, but we want to have a bounded inverse. So, and A minus Z minus 1, we know it's well defined, is bounded. So we define the resolvent set like this. It means A minus Z is boundedly invertible. Yes. Oh, sorry. No, sorry. Okay, I already did the mistake because, yeah, sorry. It's a complex number. Thank you. So we are looking at all points in the complex plane such that this is boundedly invertible. It's not easy to analyze this definition. And now I take the complement. The spectrum, still in the definition, the spectrum of A is, we usually use this, I mean, it's a common notation. It's called sigma. Sigma. Sigma of A, it's a complement. So it is the set of C minus rho of A. And I will be even more precise. It is a set of Z in C, such that either k of A minus Z times 1 is not 0, which is a negative part of this statement, or I have a second condition. So if I want the complement, it is either not this one or not this one. So it means either it is, this kernel is not 0, or if k of A minus Z times 1 equal to 0, then A minus Z minus 1 is not bounded. This is a complement. I either do the negative version of the first condition or the negative version of the second condition. So point in the spectrum, and this is really the important notion. This is I will show you that this is a natural generalization of eigenvalues. It's the set of Z such that either this operator is not invertible, or if it is invertible, its inverse is not bounded.
How is it different from the matrix?
We'll see. Okay, you haven't submitted any. So exercise for you. Not for the other one. You don't have to copy. No, it's an important exercise. Exercise. What do you do?
I don't know.
Guys, set or take H, my favorite and the simplest Hilbert space, L2 of R. You can do already everything. And a multiplication operator, by phi, so I will record what it is, phi. Let's take a bounded and continuous function on R. You know this notation means continuous and bounded. So I just rewrite it for you, m phi on f evaluated at x is m is phi of x, f of x. This is a definition of a multiplication operator. Question for you, what is the spectrum of m phi? No, you cannot answer without thinking. Nobody can do it. Somebody has a guess. Can you guess? So you have, it's very difficult to think about everything at the same time. We replace in this definition A by multiplication. And you want to have either that the kernel is not zero or that it's not bounded. We have seen an example before with this x squared plus 1, except that x squared plus 1 is not a bounded function. Can you guess what is the spectrum? Anybody?
Zero.
No, 0 doesn't play any role here. I know I'm sure you can all answer, but you need a few minutes or half an hour. No, I'm looking for a subset of C. I give you the answer, but HeavyDo is going to prove it. Answer. The spectrum of M phi is, there are different ways of writing. It's phi of R, but what means phi of R? It is the set phi of x for any x in R. So it's an image. So if I plot a function phi, if I plot such a function, what is the image? It is, what is the minimum value? Let's say it stay here. The image is going to be this interval. This would be the spectrum. Why? Because essentially you have to look at 1 over phi of x minus z, and you want this expression to be a bounded expression, to be bounded. So if this is 0, then it's becoming very big. So the only way such that it becomes non-zero is that z is very different from phi of x, or it's becoming unbounded precisely when z is in this set. Okay, HeavyDo is going to write a precise report, but remember, for multiplication operator, the spectrum is the image of the function. In fact, you can even write it as range. It's not probably not standard, but it's a range of phi, the image of phi.
That be not standard.
I'm not sure people use this notation.
It's easy to understand.
Yeah, it's easy to understand, but I don't think we use it so much. And observe that I've taken a function, on this picture, I've taken a function with real value. But I could perfectly take, except that the picture is more complicated, but I could perfectly take a function phi with value in C. And then you have to look at the value of Z such that this is not bounded. But the answer is the same. This could be, I'm not saying that this is in R. On this picture, it is in R, but it can be in the set of complex numbers. So it's not difficult, but you have to carefully look at all definitions. So why is it a generalization? Yeah, I can move to this. Why is it a generalization of eigenvalues? So first I need to recall the definition of eigenvalues, not only for matrices, but in the general case here. So definition. Let A, D of A, be a linear operator. Z, a complex number, is an eigenvalue. You should be able to write this definition. Is the eigenvalue of A if there exists F, be careful, in the domain of A, such that AF is equal to ZF. And I'm assuming F is not 0. Otherwise, it's a little bit stupid. This is a definition of an eigenvalue, which you know from linear algebra, except that for linear algebra, A would be a matrix. And in this case, you don't have to care about this notion of D of A because it's everything. But you would have the same equation. Right? Do you all agree with this definition? This is a natural notion of eigenvalue. Okay? And we call F the eigenvector. F is called either eigenvector or eigenfunction. Is called the eigenvector or eigenfunction. You see, German is also important, not only French mathematician, because eigen is from German. Not everything has been discovered by French people.
I thought you'll be more proud that everything was discovered by them.
No, I'm not proud of this. No.
National problem.
I don't care about national pride. What is the meaning? You cannot decide where you are born. This is imposed to you. Remark or lemma. Who has not submitted anything? Yeah, I know, but you have already something. Sorry, I need to finish this definition. The set of all eigenvalues, is denoted by sigma, but be careful with the index key of A. E is for eigenvalues, of course. This is the notation. Can you guess why P? No, this is not German. P here is for point spectrum. P is for point spectrum and sigma is for spectrum. So the point spectrum. So the set of eigenvalues is just denoted by sigma P of A. And be careful, it's a subset of C. because the spectrum is it's a complement of a set in C, so it is also something in C. Lemma, the point spectrum, so the set of eigenvalues is always in the spectrum of A. This is a one-line exercise. Why? Check the definition of spectrum. Somebody has to be in the kernel, but precisely if we have somebody in the kernel is not empty, it's not just zero. It's really a one-line proof. Just check. So it means what we know from linear algebra is a subset of what we are learning here. Okay, the notion of spectrum. But this notion of spectrum is really more general because look, for M phi, for this, let's take an example. And a question. What is the spectrum of this M, the sine function? I take the sine function just because it's easy, which is? Thank you. -1, 1, this is the image. What is the point spectrum of this M phi, M sine? Do you have a solution of this equation? Sine, because I replace A by multiplication by sine. So do we have a sine times F is equal to ZF? Do we have a solution?
Other than 0, no.
So why 0? I said F cannot be 0. So what is the point spectrum of this operator? Empty. There is no solution. Try to solve this equation. Sine of x, f of x is z f of x, but be careful, it's not for single x, it's for all x. It's an equality bit as function for any x belonging to R. Do you have a solution of this equation? And F is in L2 of R. Can you find a Z which satisfies this for all X? If you are able to do it, you are very strong, but no, it's not possible. So no, there is no solution of this equation. Remember, a function in L2, you can change it at a countable number of points. So don't tell me that f is just the function, let's say 1 at a few points and 0 everywhere else, because this is not a function in L2, this is a 0 function. So no, there is no solution of this. So the point spectrum is 0 for this multiplication operator, but its spectrum is still. So new question for anybody? It's an exercise. Find phi bounded and continuous. CB. So that the point spectrum of M phi is not empty. And let me make it even more difficult. The point spectrum of M phi is zero, 1 intersection with Q. This is more challenging. Find a function such that the point spectrum of this multiplication operator.
Second one shouldn't.
No, yes, it makes sense. The point spectrum is all rational numbers between 0 and 1. No, it's okay. Sorry, it's two separate examples. This is easy. This is less easy. Sorry? Yeah, the first, yeah, the answer for the first one. Oh, no, sorry, it was not empty. Not empty. Yeah, otherwise this is too simple. No, not empty. Anything but not zero. Not empty set.
Take the function one. That's boring though.
It's boring. Find another example. And then this is more challenging. I let you think about it. And question, can you find an example such that you got 0, 1? Point spectrum, be careful. Of course, the spectrum, this is easy. Take absolute value of sign, you get it. But the point spectrum. If somebody can prove this, I will be happy. So now you know how to make me happy. Find this, the solution. Okay, I'll let you think about it.
Exactly the same as eigenvalue.
I define everything. The point spectrum is the set of all eigenvalues, and I'm looking for multiplication operator so that it's not empty. Now this is more difficult, and this is even worse. Exercise, one more exercise. If this is more general in the sense I'm not only considering multiplication operators. With multiplication operators, a good point is you can make everything explicit. But there are operators which are not only multiplication operators. For I take a B bounded, show that the spectrum of B for any operator is, sorry, I said it's a subset of the complex plane. This is, let's say, the spectrum of B, but I can impose something on the size of this set. B, sorry, I need to change the letter. I'm going to have too many B. This one I cannot change because B of H. So let's take A. This is included in the ball of radius norm of A, centered at 0 in the complex plane. So it means this spectrum of A, I'm claiming that it is included in a ball of radius norm of this operator, which is well defined because it's a bounded operator. And what is the key for proving this? Use Neumann series. I introduced the Neumann series last week. Can you remember what it is? It is stupid equality. 1 minus A minus 1 is the sum of J from 0 up to infinity of AJ, which you know for numbers, but there is a condition. Not A, but norm of A is small, strictly smaller than 1. Observe, I'm not in this framework, but what you can always do, you can always consider A divided by 2 times the norm of A, if necessary. So if you divide by 2 times the norm of A, then it's smaller than 1. Its norm is smaller than 1. So you can come back to this easily. Or you divide by a number sufficiently big so that it's smaller than. Yeah. In fact, I'm not even sure that you need the Neumann series. Yeah, you can use the Neumann series because if you get A with a norm smaller than 1, you know that you can apply this. So you know it's invertible. That's how you can use it. You don't even need this, but you can use it. Any question or remark? So now, yes.
operator, especially the eigenvalue. If we think about eigenvalues in matrices, we have also eigenspaces. Do we have also a concept of eigenspaces?
Very good question. So let me rephrase it for everybody because they couldn't hear you. For matrices, indeed, when I write, so if F is a matrix, if A is a matrix, AF is equal to ZF. As he said, F is an eigenvector. Do we have the same thing? Question. What about Z in the spectrum of A, but not in the spectrum, in the point spectrum? That's your question. What happens if now it's no more matrix? By the way, for matrices, you can see that these two sets coincide. So I need to go to infinite dimensional if I want to have something different. What about Z in the spectrum of A, but not an eigenvalue? Do we? Of course, we don't have this. Can we still say something? This is a good question. I was not planning to do it, but it's I think it's a lemma. Or no, it's not easy, but let me try to remember it. If Z belongs to the spectrum of A, any operator, there exists a sequence Fn inside the domain of A, n is in N, such that AFN, this is well defined, is approaching in a suitable sense to ZFN. This is what we can do as n goes to infinity in a suitable sense, which I will not recall because I need to check carefully. But it means you don't have this, but you have an approximation of this. If you think about it, it means this is well defined. It's approaching ZFN. And yeah, I can make a picture about this for multiplication operator. It's just a picture, so don't take it too seriously. Take again H is equal to L2 of R. Let me take phi. I already mentioned this example. Hyperbolic tangent of X, or hyperbolic tangent, because it has this shape. Okay, this is hyperbolic tangent. So I consider M phi. Can you guess what is the point spectrum of M phi? If you remember this sine function, the point spectrum of F phi is also empty. For the same reason, you cannot find a solution of this equation. What is the spectrum of Fm phi? Now you should know it because Heavido has proved the theorem. What is the spectrum of? Yes, good. -1, 2. So in particular, let me take the value 1/2. 1/2 is inside. This is arbitrary. 1/2, we have 0 here. This is 1/2, right? I don't know what is this value x, but there exists x0 such that the hyperbolic tangent of x0 is 1/2. So we don't have there is no F in this Hilbert space, so that hyperbolic tangent of x, f of x, is 1/2 f of x. Otherwise, it would be an eigenvalue. But what is the picture I wanted to do is you can construct a kind of Dirac sequence. You should remember Dirac sequence are this set of functions converging to a delta Dirac distribution. So what is this theorem? It says you can construct a family of functions still in the Hilbert space. This is, let's say, F1, F2. They are all in, here's a domain of, or the spec, no, sorry, the domain, where is the domain? Yeah. For this example, you don't need, the domain is everything, so there is no constraint. But you can construct a family of function in H such that you can check A, Fn, so A is just multiplication by hyperbolic tangent. Applied to F is essentially this 1/2 times F. Because if you are close enough to this x0, this hyperbolic tangent is essentially 1/2. The closer you get to x0, the more this function will take the value 1/2. So in this sense, you don't have an eigenvector, and this is important. I mean, it's an approximation of a point in the spectrum, but not in the point spectrum. But the theorem is more general, and it's, if you want a reference, you can look at Weil sequence. I think this is the correct name. It's a sequence of functions which converge to any point in the spectrum, but not in the point spectrum. All right? Does it answer your question?
So we have all the components of the sequence, all elements of the sequence, and they are like description of A, then that's our.
Yeah, except that on this example, I can do a picture explicitly. If you give me a general A, the theorem tells you you can construct such a sequence, but most probably I cannot make a picture of it because it's not a multiplication operator. So I won't be able to see that really this sequence of function is approaching this x0. But still, there is a theorem like this. Yeah. This is true. And so what? You want, good point. I never touch the value 1 or -1. So you would like to have it open, right? Please do an exercise why I need to make it close. Because if you keep this in mind, now push this function close to infinity, you will be as close as possible to 1. And at the end, you will not touch 1, but you will be as close as possible to 1, so you need to take the closure. So it's correct to take the closure. In fact, I can lemma for you. Let me state it more precisely. The resolvent set is open in C, which is equivalent to saying, because it's a complement, the spectrum of A is closed in C. This answers your question. If you prove this lemma, you know that you have to take the closed interval. And indeed, it's correct. Showing the first is easier than the second one because the second one is a complement. So if you show the first one, you have automatically the second one. Now, the most important theorem for quantum mechanics, let A, E of A, be self-adjoint. One, the point spectrum of A is always real. So the set of eigenvalues is real. The full spectrum of A is also real. And this is why self-adjoint operators are so important in quantum mechanics. You can only measure something which is real. And you can only measure things which are in the spectrum of a self-adjoint operator. I put the proof of this in the notes because it's such an important result. I'm not going to present it, but it's very, very fundamental. So if you have some time during the break, look at the proof. It's not difficult, and it's really essential. And there is a third point which is more or less related to your question. If F1 is in the domain of A, satisfy AF1 is Z1 F1, and take a F2 in D of A, which satisfies AF2 equal to Z2 F2. And I assume that Z1 is different from Z2. So you have two eigenfunctions corresponding to two different eigenvalues, right? What you know from linear algebra, these two eigenfunctions are orthogonal. You have two vectors which are orthogonal. The same is true here. Then F1 is orthogonal to F2, like in linear algebra. Yes. Yeah. See, I'm not sure I understand. Oh, say it again.
And there is an eigenbasis
For the same Z. Okay, okay, understand. So there are two things I should add. First, if Z is in the point spectrum, this doesn't answer your question yet. If Z in the point spectrum, then it is possible, I mean, they might exist. Then it is possible that Z is of, no, is of multiplicity, let's say n, and what would mean the multiplicity n? It means there is n linearly independent vector which satisfy A, one of these vectors is equal to Z, this vector. So it is possible that Z is of multiplicity n if there exists F1 up to Fn linearly independent. Such that AFJ is equal to ZFJ. So this, but this doesn't answer your question, but we have this natural notion of multiplicity. The multiplicity can be 1, it can be 25, it depends. Okay, the same for matrices. Now, your question is, can we have a basis made of eigenvectors? So remark 1. Remark 2. The set of eigenfunctions span a vector space H P of A. Let me just say it again what it is. I introduced this notion of vector of fj eigenfunction. The set of eigenfunction, you can generate a vector space with f1, f2, f3, and so on. Question, and we denote this space, it's quite natural, by h with the index p, and of course it depends on your operator, because these are eigenfunctions of one operator. Question, is this equal to h? Is this your question? The answer is, in general, no, because we have seen an example where you have no eigenvalue. The sine function, we have seen that it has no eigenvalue. Still, the Hilbert space is L2 of R. So in general, it's no. In general. But yes, who knows an example where it's true? No, I'm only speaking about self-adjoint operators here. Yes, I'm in this framework of this theorem. Do you know any example where it's yes?
Just take one.
Okay, you can take the operator one. What is the eigenvalue? It's one, and everything is a vector, is an eigenfunction. Okay, but be more something more fun. Can you guess an example? You heard about the harmonic oscillator. Probably you know the harmonic oscillator. Yes, for example, the harmonic. I will speak about this in a few minutes. Oscillator, where you have only eigenvalues. You have no spectrum, which is not an eigenvalue, which means you have an equality here. Okay, let me continue. Otherwise, I will never finish. I have a short section with a few examples, and I will make it even shorter. There are more information. You can find more information in the notes. 3.7 examples of self-adjoint operators. Example of self-adjoint. We have already seen many. So let's take L2 of Rn. There is no reason to stick to one dimension. Take L2 of Rn. And M phi, multiplication by phi, which is now a continuous unbounded function in Rn. By the way, I don't need continuity. I don't need boundedness. I just take it for simplicity for now. Can you tell me what is the condition on phi such that it is when is this self-adjoint? Is self-adjoint. I mentioned this already last week. No, I could not because I had not introduced the notion of self-adjoint. When is it self-adjoint? Yes, if it is self-adjoint if phi takes real values. So it means phi of x is a real number for any x in Rn. This you can easily check if you don't believe it. Look at the definition of the adjoint. It goes in another, on the other side of a scalar product. It takes a conjugate. So you get it self-adjoint if and only if phi takes real value. So it means any multiplication operated by a real valued function is self-adjoint. Now, what about if phi is in L infinity of Rn? What it means just bounded. I introduced this already a few weeks ago. It means just bounded, no continuity. The same result. Same result for phi real. So you need a real valued function such that it is self-adjoint. And now if phi is not even bounded, take any phi, measurable. What can you say in the general case? For general phi, for general phi from Rn to C, but I need this notion of measurable. And we know what is the meaning. Then I define M phi, but I need to be careful. I need a domain. Otherwise, if you multiply a F by phi, you may go outside of the Hilbert space. So what is the domain of M phi? The domain of M phi, you just look at the definition. It is a set of F in L2 of Rn, such that the integral of phi of x, f of x, modulus squared dx is finite. Because this is how you end up in the Hilbert space when you apply M phi. This is, and it turns out that then M phi is self-adjoint with this domain. So now we have a domain is self-adjoint if and only if phi is real value. So the same statement, except that we have to be careful about the domain. Okay. This is not completely trivial. I mean, proving it for bounded function, it's fine because you can take it outside of an integral and so on. For unbounded, you have to be slightly more careful. But this is true. So we know quite a lot of self-adjoint operators, which are multiplication operators. Okay, this is the first example. So far, so good. Do you know any other one? Any self-adjoint, bounded or unbounded? Well, I have never spoken about Hamiltonian. Yeah, because people have worked for this, but second type of example, this is called, so this was sorry, I should have mentioned here, multiplication operator. And we have already seen this, multiplication operator. We have already seen this. What about differential operators? I have not spoken about them, but in fact, you know them, differential operators. Okay. You remember in this chapter on distribution, I have introduced the Fourier transform. And I just recall a formula, the Fourier transform of f evaluated at x is in 1/2 pi n over 2. I'm still in L2 of Rn. Integral of Rn e minus I x psi. Oh, and I need xi here. F of x dx. This is a Fourier transform I mentioned already a few weeks ago. And it was defined on the Schwarz space, but I mentioned this F is unitary. And now we know the meaning of unitary. We have seen it a few weeks ago, or maybe last week or 2 weeks ago. Is unitary on L2 of Rn. which means it maps L2 of Rn on L2 of Rn bijectively and isometrically. So if you apply F, you don't see any change. I mean, you start from H, you get back to H. So question. What is the difference? In the chapter of distribution, I mentioned one more thing. I mentioned, so in chapter 2, I mentioned this there is a nice report on the website. Fx applied to F is equal to, who remember or who knows this? No, yes. What should I put here? You should remember. Maybe you should also remember. Minus, it's in one dimension. We did it in one dimension. In chapter 2 in L2 of R. So it's just multiplication by one variable. Minus I d over dx. It's a derivative. This is in the chapter about distribution when you apply, and this was true for F in the Schwarz space. If you take Fourier transform of x times F, it's the same as taking the Fourier transform and applying derivative. And this is not difficult to check, at least at this level. Right. Now, in L2 of Rn, I can do the same thing. We have f xj f is equal to minus I dj Fourier transform of f. Do you understand what is the meaning? I look at the coordinate j. So this is multiplication by the coordinate xj, and you take the derivative with respect to the variable j. So this is true for j from 1 up to n. So we have this. All right. So why I recall this? Because I can play with this. This x, or this xj, is a multiplication operator. Just what I introduced. So I can look at, we can define the operator minus, no, let's do it like this. We can define the operator. I will do it in the same order. F star xj f. Think of f star is just, it's a unitary, so it is an inverse. And I'm claiming that this is the operator minus I dj. Think about it. What I'm saying, we have an operator. What I do, I sandwich it with Fourier transform. So first apply Fourier transform, xj, and then the inverse of Fourier transform. And if you look at this, you can check. How you check it, you need to, you need to play with Fourier transform adjoint. But this is equal to minus I d over dxj. This is a new operator. The derivative is a linear operator. Take a function, taking the derivative is a linear map. If you take the sum of two functions, take the derivative, it's a derivative of the first function plus the derivative of the second function. However, we have to be careful about one thing. This guy has a domain. So it means this guy on the right has also a domain. And indeed, if you take an arbitrary function, you cannot take its derivative. It's not well defined. You can only take derivative of some functions. So what is the domain? And I will stop here. So we define the linear operator minus I dj. And what is the domain? Probably you can see from here. When you apply it here, when you apply this to a function, it's like taking Fourier transform and then xj. But you can apply xj only if, after the Fourier transform, you are on the domain of this guy. So it means this domain, be careful, it is f star domain of xg. It looks complicated, but take a f here. Take a f here. What does it mean? It means if it is a Fourier transform of a certain domain, it means f is equal to f star of g for g in the domain of xj. All right? And now take this f and apply here. This guy on f is the same as this guy on f, but f is equal to f star g. So when you apply this on f star g, you have Fourier transform on its inverse. They cancel, and you get xj apply on g. But I can do it because g is in the domain. Okay, so this is a differential operators with its domain. Why I present it like this? Because it's more difficult to have a feeling about this domain. I mean, the feeling about the domain of xj is it's easy. We know it's a set of functions so that you can integrate when you multiply by xj. Now, this is a subset of the Hilbert space. You need to take the Fourier inverse of this, and it gives you the domain of this. It's well defined, even though it's less explicit. Multiplication operators are very explicit. Differential operators are less, the domain is less explicit. On the other hand, this is quite explicit. You take a derivative, but the result of this derivative has to be in L2, which is not so easy. Okay. So I know it's slightly abstract. I will not spend too much time on this. Next time, I will just finish one or two examples. Why I introduce this? Because we have the Laplacian. The Laplacian is a very useful operator. It fits into this framework. Why? Because instead of xj, I take x squared. So I want to finish with Laplacian next week. And just mention, indeed, the harmonic oscillator is made of Laplacian plus multiplication operator. And so next time is already the last lecture. So I will just finish with these examples. What is the last topic? For a self-adjoint or Hermitian matrix, you know you can diagonalize it. You take your Hermitian matrix, you can there exists a basis where it's diagonal. Can we do the same in this framework? Yes. We can diagonalize any self-adjoint operator. We cannot diagonalize any symmetric operator. This is not true. So self-adjoint are much more important than symmetric. Okay. Sorry for these 5 minutes.